Hello there. Just when you think you're done with a project, another video is born. After my last video on tuning musical systems different musical tuning systems, I kind of thought I was done with this, and as I was going through my folders and cleaning up all of my information, I stumbled upon a spreadsheet tab about calculating interval tables, and I thought, should probably finish this tab up while I'm at it. And as it turns out, it was a missing puzzle piece to this series that has given birth to a new video, which I really do hope this will be the last thing I have to say on this, because this has been a big project. So we're going to look at intervals here in the generic sense. And here is a graphic showing that we have an interval always starts off with a defined unison, and then the interval is the mathematical distance it is between every other note contained within it until you get to its octave. And every note has its own interval scale. So here's an example of intervals here using Pythagorean tuning. If we start at C -5, which is not on the keyboard, but you can certainly mathematically expand the keyboard out in any direction you want. In Pythagorean, we define C as binary, which means if you have it enough times, it will become 1, the number 1. So good place to start, right? So it's C -5. Having a value of 1. If we want to look at perfect fifth relationships up the keyboard, the first perfect fifth would be G -4, and that's what that red line indicates there. It goes from C -5 to G -4. That's the first perfect fifth on the keyboard, the theoretical keyboard here. Then from G -4 to D -3, that would be the next perfect fifth. And D -3 to A -3 would be the next perfect fifth. And if I was to start at any of those other notes on the scale, all those other green ones, those are just showing all the other perfect fifths that are listed there within 2 octave ranges there of C. So that's one of the intervals, the perfect fifth, but you can do this with all of the intervals. So we have here, just a refresher, we have the geometrical mean square root of 2 relationship that in equal temperament shows you how all these notes have this relationship between each other, where if you multiply the unison by the octave, you get 2. You take the square root of them because you're multiplying 2 factors together to get square root of 2, which is your tritone. And all the intervals will have this relationship. So if we look at all the possible intervals for all the possible tones on the keyboard, there are 12. Here's what we come up with. Well, we have the minor second and the major seventh. That's our first sort of geometrical mean relationship here. Each of these is a geometrical mean to the other one, and they are all the same mathematical distance. If we look at major second and minor seventh, we see the same thing. If we look at the minor third and the major sixth, same thing. Every tone on the keyboard corresponds to the same mathematical distance in that interval as all the rest of them. Same thing with major third and minor sixth, perfect fourth and perfect fifth. And then within our tritone, the tritone doesn't really have an interval that to compare it with other than just itself. So then here's what we can say here about equal temperament being what we use today. It's the only musical tuning system that is based on mathematical perfection. It is the ideal that music would be structured at, mathematically speaking. It does use irrational numbers to generate non-whole tones for all of its semitones, except for whatever you're using as your seed value for tuning. This is generally seen as The biggest drawback for equal temperament is the fact that you don't generate whole numbers for your whole notes, except for the one you're tuning off of. And that's pretty much the only drawback to equal temperament. It uses one recursive multiplier, which is 2 to the power of 1/12, making it the only true geometric increase when generating your musical scale. This is pure geometric increase. So it has only one possible absolute multiplier for every interval. You do not have expanded or contracted intervals in equal temperament 12. And if anybody says you do, they're wrong. They're just using nomenclature that's from a bygone era. There is no such thing as an expanded or a contracted interval with equal temperament. That is its benefit. It is mathematical perfection, so therefore you don't have to adjust for that. And it's one of the reasons why changing keys in equal temperament is so effortless. And every octave adheres to that geometrical mean inverse relationship. Every octave does. Once again, the benefit of mathematical perfection. All right, so let's talk about some fun facts with equal temperament. The median interval is the square root of 2, which also happens to be the length of the diagonal of a 1, 1, root 2 triangle, or the diagonal of a square. Kind of an interesting connection to geometry there. Another fun fact, tuning A to 432 hertz, it is meaningless in equal temperament. Doesn't do anything. You're always going to generate irrational numbers no matter what your seed value is. 432 or any other number has the exact same effect in equal temperament, which is to say nothing. There's no significance between what value you tune A to in equal temperament. There are some other interesting qualities to equal temperament, though. One is when A is tuned to 440 hertz, you get a red, green, blue manifestation if you are mapping color to notes. And it's the only tuning of A that generates a pure blue. So that's kind of I think that's kind of a fun reason for wanting to tune to 440 hertz. And then I also demonstrated in a prior video about color mapping that when you tune A to 452 hertz in equal temperament, the F-sharp 4 octave actually is the best octave for showing the complete light spectrum from start to finish. So that makes that particular octave range kind of interesting on the keyboard. Also, if you go one step higher and tune A to 453 hertz, you're now no longer in the range of A. You have kind of crossed a boundary, and now you're tuning A to a low A sharp. So when we look at where that we find that closest approximation that A has to that inverse relationship that I demonstrated before with light right here. This here is the closest you can get, and that shows you the threshold of what the highest value for A should be. So that's another kind of defining characteristic we can use for music. Wherever we see this closest approximation to light being mapped on this octave between F sharp 4 and F5, that is the highest limit for A that is defined for that musical tuning system. All right, so those are all the interesting things there about equal temperament. Now, when I first was teaching myself about how to construct Pythagorean tuning, that's when I discovered that the F sharp octave mapped perfectly to the color spectrum. And it's also when I discovered that the recursive multipliers that are generated in that system also follow a keyboard pattern, which, if you take nothing else from that first video, I hope you take at least that much, because The recursive multiplier trick, I think, is one of the keys for unlocking some of these confusions that people have about musical tuning systems. So what I did is I took those recursive multipliers, okay, and for those people who have a little trouble visualizing, I have decided to try to make this a little easier. So I got a little keyboard pattern here, and I put in those recursive multipliers. And if you look there, you notice that 256 over 243 always falls on a white key, and 2187 over 2048 there always falls on a black key. That's what I mean about how that recursive multiplier pattern literally follows the keyboard pattern on the piano keyboard. So I don't think it's arbitrary that the piano keyboard was designed how it is, and I've heard other people make some guesses as to why they thought the keyboard on the piano is the way it is. I think this is the correct reason why. I don't think it's because of Fibonacci sequence or just because, well, it just makes it easier for you to find your place on the keyboard because there's some visual cues that kind of break the keyboard up. I mean, I'm sure that helps, but I don't think that's a reason why it was done. This is the reason why it was done. These mathematical relationships of the recursive values as you go up the scale in Pythagorean tuning are what this keyboard is based off of. So here I filled in some values for those keys that are the common ones used in Pythagorean tuning if you tune A off of 432 Hertz. And you can see all the whole notes, with the exception of F, have whole numbers. All of the black notes there have some kind of a repeating pattern. I've rounded everything to the nearest tenth for brevity, but these numbers, they go on quite longer. So anyway, so if we wanted to look at a particular octave, so let's look at C like we were doing earlier. So I put in here the boundaries between the octave of C here, starting with 512 there, 512 Hertz for C being the unison, and then 1024 Hertz for C being the octave. And if we look at the recursive values there, we can multiply them together to find what each interval is in the octave of C. So as the key down below lists, if you're starting with a value of 512 Hertz for C, you multiply that value by what you see on that key there, the 256 over 243, and that will give you the C sharp value of 539.4 Hertz for the black key above it, the C sharp. You take that 539.4, you multiply it by the value on the black key, the 2187 over 2048. That will give you the value for D, which is 576 Hertz. Okay, so that's the pattern we're going to follow here for how these numbers are generated. Now, the absolute interval values up at the top there, on that top keyboard, those are each determined by starting with, if your unison there is 1, you would then multiply it by whatever the next recursive is. So, right, so we're going to start with 1. We're going to multiply 1 by 256 over 243. And that gives you the first interval, 256 over 243. Now, to find the major second, we would take 256 over 243 times 2187 over 2048. And that actually comes out to be 9 over 8. And this is how each of those absolute fractions is generated. It's just you multiply however many of those recursive values together that matches the corresponding keys on the top to get that top fraction. Then whatever your C value is that you're starting with, in this case 512, that will then get multiplied against each of those absolute fractions, which will get you the same numbers as the recursive fractions does. So I'm just kind of showing you how this is all constructed. Now you notice the tritone is colored red. The tritone is a little bit different here. We're going to talk about that a little bit later on. But every one of those other values is what I would call the optimal interval value for Pythagorean tuning, which is the C octave. If we looked at a different octave, now we're going to look at A. So the octave of A, as you notice here, has lots of red values. We have some values that are the standard values, those pink and those blue ones, but those red ones, those are generated. So for instance, let's look at the major third there. 8192 over 6561. How is that number being determined? Well, we're taking 256 over 243 on that bottom A there, on the bottom keyboard, multiplying it by the A sharp 2187 over 2048, multiplying that by 256 over 243 on the B, multiplying that by the 256 over 243 on the C. That will give you the 8192 over 6561. Okay, so that's how these are being generated. And whatever it is whatever it is. The math doesn't lie. You put the numbers in, an answer comes out, that's the answer. The A octave is kind of interesting in the regard that we have established in prior tuning videos that there are key intervals that were very significant in the Pythagorean tuning, and that was the major second being 9 over 8, and its geometrical twin on the other side, the inverse relationship of 16 over 9 for the minor seventh. And then the perfect fourth of 4/3 and its geometrical twin there, the 3/2 for the perfect fifth. So what's interesting in the octave of A is those intervals always correspond to, and only in this octave, correspond to the 2187 over 2048. Those are being generated by that particular fraction on those black keys. So there's kind of an interesting mirroring of these two systems in the A octave. And A is the only octave where you see this happen. So it's kind of, I think it's somewhat interesting and maybe might explain why people like to tune off of A instead of C. But that's just a hunch on my part. I can't prove it otherwise. Anything else is just kind of an interesting observation. But as you see, if you're actually following the recursive patterns, as the recursive patterns follow the keyboard, then A generates some really ugly numbers, right? But it's the recursives that matter, not the absolutes. So let's look at some of the intervals here in Pythagorean tuning. I'm going to start with what I call the strongest interval patterns here, which is the perfect fourth and the perfect fifth. And if we look here, first at the top we see I have the actual mathematical pure value there of the 2 to the 5 over 12th power and 2 to the 7 over 12th power. That's mathematical purity. And I want to know, how well does this rational system approximate mathematical purity? And in Pythagorean, we get rounded to the nearest hundredth, is what I'm looking at here. These all are good approximates, aren't they? Now, they're not perfect because we're rounding. And down below, you can see I have a standard deviation listed. So that is basically how well does this entire interval, with every note possible, approximate equal temperament. And you can see it does a pretty good job. If it doesn't, I color it red. If it does, I color it white. So you can see there's only one red value here, and that's the F sharp octave. When we go to F sharp to B, that interval there, that perfect fourth, is actually an expanded perfect fourth. And if we look there, we get 1.35 instead of 1.33, which means being slightly larger, we're kind of overshooting where we would like to go. We've gone past the 1.33 and we've gone a little bit further. So that's referred to as expanded. And then if we look at the other side, we have B going back to F sharp, which if we overshot one way, then that means that we're going to be slightly less going back home. So we refer to that as contracted. Now, in prior videos, I made a claim that is, I understand now is erroneous, and that was that there was no Pythagorean comma in this system if you constructed it correctly. Before doing this interval project, the way I understood the Pythagorean comma was as one creates an octave, there's a very, very slight error that gets introduced, which isn't apparent at first, but as you start going up or down the scale, that error starts to compound until you reach a breaking point, at which point things start going out of tune. That's kind of how I understood the Pythagorean comma. And the way I was constructing this, my octaves were all perfect, so I didn't see anything go out of tune. I thought that there was no Pythagorean comma. How I understand it now is you cannot have perfect fifths that return to an octave. They will always be slightly off. If you go far enough down the keyboard on perfect fifths, you never, ever return back to your starting point. And that is true. But that's true for all of the intervals. But in any way, so the Pythagorean comma right there is the contracted perfect fifth, which gets you 1.48. And you can see that really, really ugly fraction there. That's the Pythagorean comma. And you can see its geometrical mean inverse is on the other side there at the expanded perfect fourth. Well, the expanded fourth, I guess. And so anyway, as you can see, all the other intervals in Pythagorean tuning for the perfect fourth and perfect fifth work just fine. There's only one that has to be compensated for because it's slightly off, and that's, once again, in the F-sharp octave. So that's why we refer to these as perfect fifth and perfect fourth, because the 4/3 and 3/2 is clearly the most dominant value, with one exception. Now let's look at the other intervals here in Pythagorean tuning. So we have the major second and minor seventh. I brought this one up next because this is the next most dominant interval in Pythagorean tuning. And we see this is the other significant one, the 9/8 and the 16/9. So these four here that the two in the prior one and these two fractions here are definitely those key values. And you can see they are clearly the most dominant. Now in this case we have two exceptions. We have two contracted major seconds and we have two expanded minor sevenths. And once again, they have their own geometrical means on both sides that correspond to all the everything's always going to have a geometrical mean relationship between the major second and the minor seventh. It's just a matter of, is it going to be your default, your value, your most dominant one, your smallest fraction, your closest approximate, or is it going to be an expanded or contracted? Now, if we look at the major second, notice how mathematical purity is 1.12. We do not have any values that actually round to the nearest hundredth at 1.12. It's either going to be slightly under the contracted version at 1.11. Otherwise, in Pythagorean tuning, the best you can do is 1.13. But hey, close enough, right? Now, if we look at the other side, the minor seventh, we can see 16/9 actually rounds to the nearest hundredth, to the exact same number as mathematical perfection does. We do have that expanded value, though, which kind of overshoots it a bit much. I mean, it's two 1/100ths, off, which, even 1/100th off, you're probably going to notice. Your ears will probably notice. So being more than that is going to be even worse. And you can see it has a little bit of a higher error for the standard deviation as far as its ability to approximate mathematical purity. But hey, it's still a very dominant, these are both dominant intervals. All right, so now we look at the minor third and the major sixth. These have three exceptions to the rule. And, I'm not going to keep belaboring the point. I think you can all follow now. On the minor third side, most of them round to 1.19, which is the same as you would round to get mathematical perfection, with only three exceptions, which are just 1/100th off. Then the other side, it's either too high or too low. You don't have any that round to the nearest hundredth for mathematical perfection. And we see the error is starting to compound at the bottom there too. We're getting larger error numbers. So the next one, major third and minor sixth, has 4 exceptions to the rule. Feel free to pause the video and look at your own leisure. And then the final one here, we have the minor second, the major second, or I'm sorry, the major seventh. And these have 5 exceptions. And anyway, as I was doing this, it's kind of interesting how the Pythagorean tuning, when you look at something like this, it almost kind of reminds me of when people do DNA testing and they show different the structure of DNA and stuff and how it corresponds to the different nucleotides and how there's sort of 4 letters, but they always have their corresponding opposite on the other side. And it kind of reminds me a little bit of how DNA is sequenced or how it looks when it's modeled. I'm not saying DNA is musical or anything. It's just kind of funny how some of the structures of music, when you look at them, they kind of inspire or correspond to certain structures we see in other places. And in this case, it kind of reminds me of how DNA sequences look. Now we get to the tritone. The tritone is very interesting in Pythagorean tuning. First, if we look at it, it's actually symmetrical on the x-axis. If we drew a line through the middle there where those 2 middle white or 2 middle yellow lines are, you can see that everything on the top is mirrored on the bottom. Now, some of them I've colored white, some of them I've colored red. What do we notice about those 2 different colors there? Well, all those white ones, which is 1024 over 729, they all correspond to a whole note going to a tritone, which ends up on a sharp, with one exception, and that is F. When we go from B to F, we are also on that same 1024 over 729. All of those red ones correspond to a sharp going to a whole note, with one exception, and that is F going to B. All right, I've talked before about F being a quasi-whole note. It's not really a whole note, and I know some people are probably pulling their hair out when I say that, but F has way more in common with sharps than it does with whole notes. It never generates a whole number, and here in the tritones, it's clearly in the same group as the sharps as well. So F is kind of a quasi-whole note. And in fact, if we look here, one of the things about the tritone is that there is no dominant fraction here. We have 6 instances of the 1024 over 729, and then we have 6 instances of the 729 over 512. So there is no dominant fraction. They're equally weighted here. So we have 2 that are sort of competing with each other on equal terms here. Now, if we look here at this table, there are 2 octaves, the F octave and the C octave, which are the only 2 octaves in Pythagorean tuning that do not have any expanded or contracted values in them. Now, I call that an offset fraction, right? So the offset fraction you can see on the right, and then the dominant fractions you can see on the left, and they have numerators that are green. And if we start at the perfect fifth, which has the lowest numerator, we can have them go down in ascending order, and you can see each one gets slightly higher than the last one until we get to the tritone, which in F is 729. And then we can also see that the corresponding offset fraction in that interval family would start with the largest fraction, 262,114, which is the Pythagorean comma. And then for every interval after that, it would descend until you get to the 1024 numerator in the tritone as well. For C has all the same dominant fractions that F does for all of its intervals. The only thing the C octave and the F octave that differentiates them is the fact that The F octave uses the tritone 729 over 512, where the C octave uses the tritone 1024 over 729. So it's kind of like they swap. And it kind of reminds me of back in my computer days when I used to make Ethernet cables. And we used to have something called a crossover cable. Whenever you were connecting two nodes that wasn't using any kind of a router in between them, you had to use a crossover cable in order to translate between the two. And the tritone kind of reminds me of that crossover cable in order to connect these two different octaves. Another way to look at it is, once again, going back to DNA, if we look at what a chromosome looks like, where the chromosome here listed is symmetrical on the y-axis, right? You draw a vertical line and you can fold the paper and it'd be symmetrical on both sides. You have a left side and a right side. Then you have that centromere in the middle that kind of bridges the two. And that sort of reminds me of the tritone between these two octaves. So if we have the C octave on the left and the F octave on the right, and we show all of the intervals, both of those octaves have the same intervals for every value except the tritone, where they're swapped out. I find that very interesting. And another thing of note that I've noticed with chromosomes is if we put a musical scale next to a chromosome, right there at the centromere is right about where we would expect the geometrical mean of music to be, which is the square root of 2, if we were to kind of put a side-by-side scaling of them. Now, I know that's not mathematically accurate. These are just sort of things that are pop into my head while I'm doing this, these musical projects. I'm sure there's probably exceptions to the rule, but it is kind of interesting how some of the shapes we see in nature do tend to correspond to geometric musical scales. Another one that pops into my head is when I see bar galaxies. It's like the bar in the middle of the galaxy kind of corresponds to that tritone in the middle, which is sort of has its own symmetrical by the y-axis, by the x-axis. Its own internal symmetry, and then you have your intervals being the left spiral and the right spiral off of the bar. Kind of another inspiration that when I look at the structure of music, how it kind of inspires other visuals for me. All right, so what can we say now? Now that we've examined all the intervals in Pythagorean tuning, what can we say? This tuning system is the only tuning system that is entirely binary in nature, including binary numbers for C. It uses two prime numbers for all of its fractions, some power of 2 and some power of 3, and nothing else. For its recursive multipliers, it uses 2 and only 2 fractions. For every interval, it only has 2 possibilities, the default fraction and then some fraction for expanding or contracting that interval. So there's only 2 possible fractions for every interval. And it only has 1 pair, or 2 fractions, of possible geometric mean inverse fractions for the tritone. And when we take those recursives that I showed you before and we match them up to the keyboard, we get 2 octaves, C and F, that show perfect default fraction geometric mean inverse relationships within all the intervals, with the only difference being that they differ in the tritone. That's that sort of interesting crossover relationship we were just talking about. We also notice that when we match recursives to the keyboard, the A octave is the only octave where all of those significant intervals line up with the one fraction there, 2187 over 2048, for those key intervals there. And what makes A 432 hertz significant in this tuning system is it generates the most whole numbers. And in fact, every whole note corresponds to a whole number when A is 432 hertz. So I don't think that makes 432 magical. I think it makes it mathematically convenient because 432 is a power of 2 and a power of 3 only when you break it down. And that's what this whole musical tuning system is. So I think it's just leveraging or exploiting a mathematical quality that in this tuning system gives you some nice whole numbers, which is convenient, especially if you don't have a lot of tuning equipment, that's very accurate or precise, like if it's 2,000 years ago. I'm sure that working with as many whole numbers as possible makes tuning a lot easier. So there's a certain convenience of it that is leveraged in this system. So if we want to look at those two octaves of F and C, here are the fractions you would want to use for your absolute intervals versus, and then with the corresponding recursives next to it. So if you want to build your octave, your scale off of F, those are the fractions you would use. A lot of people prefer C because, as I mentioned earlier, F never generates a whole number. So if you're tuning a keyboard, you want your seed value to be a whole number, right? So a lot of people like to tune off a C for Pythagorean, and that's fine. Just make sure you're using the right tritone for C. F has the ideal tritone because it's the smallest of the two fractions, but C gives you would want to tune a whole number off of C, and especially if you can recall that C is binary, that makes it even easier. So these are the fractions you'd want to use if you were building a Pythagorean tuning system and you wanted to use C as your model octave for all of the best interval fractions. Now, before I was showing you all of the error, the standard deviations for each of those intervals as far as how well it could approximate mathematical purity. So there they all are listed for every interval, and if we add them all up, we get a total cumulative error of 8.95% for Pythagorean tuning. Now, that might not mean anything just yet because we don't have anything to compare it to, but as we move along, I'm going to show you the 5-limit just intonation and how it compares, and then also I developed a tuning system in my last video on tuning that I referred to as best fit intonation, and we will look at that tuning system and see how that compares with its intervals. So then let's look at the 5-limit just intonation. We're going to take everything we learned from Pythagorean tuning that I just went over, and we're going to kind of create a method for how we're going to contextualize this now, the 5-limit just intonation, how we are going to construct it. And this is adding upon what I talked about in my last video. There were some things that I did not take into consideration, so there will be some minor corrections here to some things I had mentioned about 5-limit just intonation in my last video. So as we go along, I will point that out. So here we go. Step 1. We want to list all those desired absolute fractions for each interval that spans an octave, a generic octave. At this point, we don't know what octave it's going to be. And we want to make sure that it demonstrates that perfect geometrical mean relationship. And, we may not entirely know what the tritone may be, but that's okay. The math will tell us for us as we move along. What's important is all the other ones, that those are all listed. And in my last video, we came up with all of these fractions here for 5-limit just intonation. Because you remember there was a lot of ambiguity as far as what people were saying the correct fractions were. And I basically came up with one that said they should be this. Now, one thing I want to walk back is in my prior video, I talked about how much I really enjoyed learning about the 17/12 being a good approximation for the tritone. And I thought it would make a better tritone in this system than the 45 over 32. I have changed my mind about that, and I have gone back to the 45 over 32, and I will explain why here in a moment. But for now, just know that these are the ones we have settled on from the past video, and these are the ones that I believe are the correct ones. So then what we want to do next is, now that we have all those absolute values defined, we want to create a recursive fraction pattern out of them. So here we go. These are all the recursive fractions. And these are all generated by taking any of those absolute fractions and dividing it by the one just underneath it. So 16 over 15 is the first recursive fraction. We get that by dividing 16 over 15 over 1. 135 over 128 is the second recursive fraction. We get that by dividing 9 over 8 by 16 over 15, and so on and so forth. So that's how all of these recursives are being constructed. Now, as you see here, there's actually 3 recursive fractions that are generated through doing this. The 135 over 128, the 16 over 15, and the 25 over 24. It was not apparent to me in my last video that these would correspond to the keyboard pattern in any way. It was obvious for Pythagorean because there was only 2 fractions that just happened to be in a pattern that was very obviously associated with the keyboard. And I thought Pythagorean was the only one that did that. Turns out that it's not. This system here also corresponds to the keyboard. And gee, I wonder why I colored some of those numbers blue and some of those numbers orange on the recursive patterns. Let's find out, shall we? So step 3 is replicate the recursive fractions, right? Make a whole big long list of them, and place the extended pattern against a keyboard to look and see whether or not any of these fractions align with the keyboard. Turns out they do. All of those 16 over 15 fractions correspond perfectly with white keys, whereas the 135 over 128 and 25 over 24 all fall on the black keys, if you line it up correctly. Now, one of the things I want to say here is a fraction in the white key should never appear in the black keys, and a fraction in the black keys should never appear in the white keys. That's kind of how I'm defining this as perfectly fitting the keyboard. That's what I'm talking about. So that's what we have going on here. So now that we have all of the recursive fractions that are now fitting the keyboard, we can determine the intervals now, the mathematical intervals for every single note in every octave on the keyboard. And if we want, well, and as we evaluate, we'll see there's only going to be one octave where all of those original absolute values will occur without any expanded or contracted exceptions. And as we go along here, I will point that out. All right, so let's look at our first interval here, interval comparison. We have the minor second and the major seventh. And as you can see, there's a lot of expanded and contracted exceptions here, aren't there? 16 over 15 is still the most dominant, and its geometrical inverse twin over there, 15 over 8, is also the most dominant, but we have a lot of exceptions. Now, once again, I've got mathematical purity at the top, and then I show the error at the bottom. And in these particular intervals, we do not have any on either side that can approximate mathematical purity to the nearest hundredth. They're all colored red. And what I've done over to the side there is I've looked and I said, okay, how many of these intervals actually are generated by just the dominant fraction and not an expanded or contracted value? And you see all those red letters there, the B, the A sharp, and the A, they're all colored red. Only F and C are the only 2 octaves so far whose intervals are generated by just those dominant numbers. So if we go from F to F sharp, it's 16 over 15. If we look on the other side, we go at F sharp to F, 15 over 8. So there's no expanded or contracted values in that octave for those 2 intervals. Same thing goes for C. Let's look at the next interval pair. Major second and minor seventh. Okay, so we've got, something I forgot to mention before. Notice how now we have 3 possible fractions for every interval. In Pythagorean, we only had 2. In this one, we have 3. We've got the 10 over 9, the 256 over 225, and then the primary 9 over 8 on the one side, and same thing on the other. You can see their geometrical mean equivalent twins on the other side. And C gets knocked off the list here. If we go from C to D, it's 10 over 9. So it's not the 9 over 8. So C gets knocked off the list. That leaves us with just F. And that will remain true from here on out. Only the F octave in 5-limit just intonation. It's the only octave whose intervals are all generated through the primary fractions and don't use any expanded or contracted fractions. So let's continue to look, though. We have larger standard deviations than we had with Pythagorean in this one. Well, in all of them, actually, as it will turn out. So we look at the minor third and the major sixth. Same thing. Here we have the minor third has a few that are close at generating mathematical purity, but all the rest are all pretty far off. This is not the best tuning system for trying to approximate mathematical purity, that's for sure. All right, so we look at the major third and the minor sixth. Same story here. All the fractions are terribly off, with very few exceptions. And then we look at our perfect fourth and our perfect fifth. This being where the most dominant of the fractions are, right? The 4/3 and the 3/2 there, they definitely occur with the greatest number of frequency compared to all of the other intervals. But we still have 3 expanded and contracted versions here versus the 1 in Pythagorean. And then we have our tritone. Now the tritone here, if you notice, look at how many times 45 over 32 occurs, and then its geometrical mean inverse 64 over 45 occurs. When I erroneously decided to substitute 17 over 12 for 45 over 32 and I ran an interval table, you notice other than that one octave that had 17 over 12 changed to it, or that I changed to 17 over 12, all the other ones still maintain the 45 over 32 and 64 over 45. And when I saw this, I realized, oh, that number is clear, that fraction is clearly the dominant one here. And it was a mistake to try to substitute it with anything else. 45 over 32 occurs by far with the greatest frequency here. So that the math told me what the right number should be. And that's what I want to convey to you here. It's one thing when somebody makes a mistake to try to spread misinformation. In this case, I want to demonstrate to you how sometimes you can put forward a hypothesis, and then you test that hypothesis, and then, you know, the math tells you what reality is. And that's how science works. And so I left in my mistakes I'm not going to correct my mistake on the last video. I'm going to correct it here in this video so that people watching can see when you do this stuff, you're doing it to find the correct answers, and you should always trust the math. So 45 over 32 definitely is what the default tritone value should be. All right, so then we're going to look at F. Since we've determined that the F octave is the one that has only the dominant fractions without any expanded or contracted values. So we've got our keyboard layout on the bottom with our recursives. We have the keyboard on the top with all of our absolute values. And you notice here what I have A tuned to, which is 440. 432 does not work in this tuning system. And what do I mean by that? Well, first of all, If the point of tuning A to 432 in the Pythagorean system was to generate the most whole numbers, which in Pythagorean, that is exactly what 432 does. When you put 432 into this musical system, however, it only generates 3 whole numbers for your whole notes. 440 generates 5. So 440 actually makes more sense in this tuning system than 432 does. Also, one of the things I pointed out in my last video that I thought was ironically interesting is that if you tune A to 440, you get C being 528, which is one of these solfeggio frequencies that everybody says is magical and associated with the heart chakra and all of that, right? And you don't just get like an approximate of 548, you get the whole number. 528. You get the whole number 528 without any, it's perfect. And I was like, wow, isn't that funny? You get a solfeggio frequency out of this. Well, after I was actually looking at the expanded keyboard a little bit further, notice what the value for G is right before the A there, 396, another solfeggio frequency. So you actually get 2 solfeggio frequencies when you tune A to 440 in 5 limit just intonation. So I think that's another plus for 440 being a good number to tune A off of. But in this case, we're looking at the intervals at the top. You can see where they fall on the keyboard. So you notice for the F octave, we get all the best fractions, right? We get all those dominant low number fractions that are the ideal fractions for our intervals. But notice how our ideal intervals of the major second, the minor seventh, the perfect fourth, and the perfect fifth, some of them fall on black keys and some of them fall on white keys, right? So it's not like A, where if we shift over to A, now we have all of our key intervals falling on only white keys and corresponding with, the being generated by a black key recursive value. But we get really ugly fractions, though, for our absolute intervals. You can see them colored in red. Those ones are definitely an expanded or contracted variation of what the default fraction is for that particular interval. So you just have to be aware of that. And some people are not aware of that, and therefore when they talk about music and they talk about octaves and intervals, they are using numbers that are incorrect. They're not derived properly. I believe this is the proper way to derive all of these numbers in both tuning values and what fractions that each octave uses. So I want to sum up 5 limit just intonation. It uses 3 prime numbers, 2, 3, and 5, for generating all of its values. It uses 3 fractions for its recursive multipliers. And it has at least 3 possible fractions for every one of its intervals. Its primary dominant one, and then usually some expanded and some contracted, or some combination of both. And this particular tuning system, it doesn't sound very good if you try to change keys because of how large the error is for all of the intervals, the cumulative error. So it's kind of limited as far as music goes. And it also has 2 pairs, being 4 fractions total, but 2 pairs of possible geometric mean inverse fractions for the tritone. It certainly has the dominant one of 6445 and 4532, but then it has a second pair of fractions that it uses as well. And when aligning your recursive value fractions to fit the keyboard pattern, the F octave is the only octave that contains all the ideal, dominant, absolute fractions for all intervals. Okay, that's important to know. We saw this before with Pythagorean tuning, where the F and the C both had all of the ideal absolute fractions, with C having a swapped tritone and F having the smaller of the tritones. So we see that mirrored here again, where the F octave is the one that uses the smaller of the 2 dominant tritones, and also has all of the ideal fractions associated with absolute values. All right, and fun fact, when A is tuned to 440, which in this musical system is what it should be, not only do you get the nice red, green, blue color correspondence, but you get two solfeggio numbers, 528 and 396. So take that, all you people that think that 440 is some Nazi plot or whatever. In this particular tuning system, any other tuning for A is going to be inferior. And as I noted in my prior video, but just to recap here again, it uses all the Fibonacci ratios that correspond to music. And it also has all three trigonomic functions, the secant, cosecant, and cotangent for the magical 3-4-5 triangle. Another cool fact about it. And then I had mentioned in a prior video that how it kind of reminds me of a strand of DNA with telomere endings. And here we can see it again. You have the 15, 8, and 69, which those four numbers appear in the two first fractions and the two last fractions, and although in different order. But I just thought it was kind of an interesting aesthetic of how they looked and how it kind of reminded me of telomere endings on a DNA strand. And here you can see that right here. This is sort of like what comes to mind when I see that. All right, so there is all of the error for 5-limit just intonation. As you can see, every single interval, it's worse than Pythagorean. And it gets you the highest cumulative error when all that error is added up. All right. So we're going to play a quick game here. Are you smarter than Wikipedia? On Wikipedia, they had a table for 5-limit just intonation where they are using C as the unison, and they were showing all the possible values for all of the intervals of C using 5-limit just intonation. And as you can see here, some of these, like B flat, those two yellow ones, they've got two different fractions for those, and they have two different fractions for the F sharp or G flat. So they're differentiating between the two, right? As if they are different tones. Those green ones, and then those same thing with the orange ones there, right? So it's like they can't decide. Well, let's see if we can sort this out using what we know now about recursive values and lining them up with the keyboard. If we take our recursive values there and we only highlight the ones starting with C, and we correspond that up above on the top keyboard for the absolute fractions that are generated from those recursives, there's the pattern right there. And you can see the ones in red are the ones that are not the dominant default fractions. Those are some either contracted or expanded version of that interval. But the point of me showing you this is that there's no ambiguity here. Those are the numbers. There is no, like, it could be this or it could be that for F sharp or G flat or whatever. No, there's only one recursive fraction, or I'm sorry, one absolute fraction generated from the recursives. So if we go back here, now that we see these fractions, let's go back here and correct Wikipedia. This is what it should look like. There's no, for that octave range, it's 64 over 45 here, tritone. 45 over 32 is not one of the options that are available. Neither is the 9 over 8 for D, neither is the 16/9 over there for B flat. Those are just gone. Those don't exist for this octave. And as you can see, all the other ones worked, except for there are three other ones there for A flat, and E flat that they have the wrong fraction. And I put in the proper fraction based, once again, off of this recursive pattern that generates these absolute value fractions. So then I will quickly recap now, I talked about two other tuning systems that I kind of developed in my last video on tuning. One that I called convergent tuning, and then one that I called best fit intonation. And I wanted to see whether or not those recursive values for both of those tuning systems also lined up to the keyboard, because if they did, it would mean my numbers would need to be adjusted, because I was making some assumptions that you could overlay the absolute interval fractions over any octave, and that was a false assumption on my part. Now that I have been realizing that these intervals for these other tuning systems actually do match the keyboard, that changes where the math is going to happen. So, as it turns out, in convergent tuning, the interval of, I guess what I should say is, the recursive fractions do match the keyboard. All of the black keys will only have 16 over 15 and 18 over 17, and that's it. And on the white keys, you will only have the 17 over 16, the 19 over 18, and the 20 over 19. Now, there are some other arrangements of these recursive fractions that will also satisfy the definition that we said for what fits the keyboard, which is that if a fraction falls on a black key, it shouldn't fall on a white key either. It's either on a black key or on a white key, but it should never be on both. That's how I'm defining it anyway. There are some other octaves in this tuning system where that is also satisfied. However, they tend to fall on octaves of sharps. This is the only whole note octave that satisfies the definition for the recursives, quote-unquote, fitting the keyboard. And it just happens to be A, which we've already determined is this kind of very interesting octave where we have an alignment between the absolute interval values and all of them being on a white key being generated by a fraction from a black key. And here they all are. So they look good. And another interesting thing is, because this one also uses the fractions 5 over 4 and 5 over 3, those two fractions are only generated by the recursive value 20 over 19. I thought that was kind of interesting too. 20 being, a fraction that has 5 as a factor. So this is an interesting alignment. It's another thing that I think I like about the convergent tuning method. Maybe not as a musical tuning system, but maybe for some other more practical applications. I like the fact that this lines up so well. Now, for best intonation, what I have also discovered is that there is only one way the recursives line up in this particular tuning system that fits the keyboard. And once again, it corresponds to all of the primary, the ideal fractions for generating the absolute intervals falling on the octave of F. Just like in Pythagorean and just like in the 5-limit just intonation. For whatever reason, when recursives line up with the keyboard, F is the octave that gives you all of the ideal fractions for your intervals. And any other octave you want to find, you have to just do the math and find out what the math generates. So for instance, if we want to look at A in best fit intonation, look at how terrible it looks. It's actually similar to Pythagorean. I don't know if you remember that, but the Pythagorean had lots of ugly fractions for A. But we get, once again, that alignment of all of our key intervals being on the white keys and all being generated from the black note number. But we get really, really ugly fractions for our intervals. So you would never want to tune off of A if you're matching your recursives to the keyboard for finding out what your recursive values or what your absolute values are going to be, because you'd be dealing with really ugly fractions, like 323 over 289, or 361 over 288, 323 over 216. I mean, these are terrible fractions, right? So what can we say about the best fit just intonation now that we're all said and done with it? Well, it uses 4 primary numbers, 2, 3, 17, and 19, to generate all of its fractions. It has 4 fractions for recursive multipliers listed there. It has 4 possible fractions for all of its intervals, multiple expanded and contracted values. It starts getting messy, really, really messy. I'm not going to show you the interval table because you get the picture. I will say, though, that because this system is so good at approximating mathematical purity, that despite the fact that you have lots of expanded and contracted values and not the prettiest fractions for them either, what it does excel in is that the error starts becoming so small that your ears probably would not notice the fact that it's slightly off. So I think in that regard, if you were to base this as your tuning method for making music, it would probably sound very comparable to equal temperament. You probably would not be able to distinguish the difference with your ears between what little error there is. And then for its tritone, there are 3 pairs of possible geometric mean inverse fractions. The 24 over 17, 17 over 12 pair, and then we have 2 other pairs listed for adjusting for the errors. So, as I mentioned here, the expanded contracted fractions, they are much smaller than the one used in Pythagorean and 5-limit tuning. In fact, there are no fractions with more than 3 digits in their numerator or denominator in this system, unlike all the other tuning systems. I mean, remember the Pythagorean comma was like 6 digits. So this one, nothing more than 3, which is its strength. And when aligning the keyboard, or the recursive fractions to the keyboard, F is the only octave that contains all the ideal dominant absolute fractions for all the intervals, just like in 5-limit and just like in Pythagorean. It's the only tuning system that uses a fraction with 432 in it. We'll talk about that some other time, but it's just one of those things I thought was ironically funny, which is for the perfect fourth and the perfect fifth, one of the expanded and contracted fractions has 432 in the numerator. And then I talked in the past about how this kind of reminds me of like a cellular shell or some kind of a shell within shell within shell system here, the way this musical system looks when you look at it, at its structure. It sort of has this internal core around the tritone, and one of the numbers generates a geometrical mean, which is sort of bridges it with the next layer, and then the next layer has a value in it which creates a geometrical mean, which bridges it with the next layer, and so on and so forth. So there's like 3 distinct layers going on here, and I kind of mentioned how that's kind of interesting. And here's sort of what I mean by that. Like if you look at like the Earth or a cell, how it has sort of a core, and then a layer around that, and then a layer around that. That's kind of what this musical tuning system reminds me of. All right, and then we look at the cumulative error for best fit intonation, and you can see it is tiny, tiny, tiny compared to all the others. So once again, while it is mathematically more complicated, if you have a synthesizer or something that has some nice granularity, it can crunch some numbers to pretty far digits, and everything is in phase, it should actually sound really good, that whatever error there is would probably go unnoticed by the ear. So I want to then just quickly recap my slides, because now that I understand how these recursives fit to the keyboard, it kind of readjust some of the numbers that I was using earlier, and I want to show that this should be the final pass for all of this. Okay, here is Pythagorean tuning. We're looking at the F octave now because that's the only one that is in true geometrical mean. It has no expanded or contracted values. We see that it generates 5 whole numbers when A is tuned to 432. And you can see that 432 gives you the most number of whole numbers, with 450 kind of giving you, it's kind of the second best, and then the rest just kind of falls short. So 432 is definitely the number for A that makes the most sense in this mathematical tuning. And when we look at its standard deviation compared to mathematical purity, we get a standard deviation of 0.60%. All right, then now we're going to look at equal temperament against 5 limit just intonation. And once again, we're going to use that F octave because that's the only one that has that pure geometrical mean relationship. It's got all the ideal fractions for that. And in this regard, we're going to tune A to 440. Now you can see there are some other values for A that give you just as many whole numbers as 440. Looks like we get 425 and 435. But 440 is kind of cool because of 2 reasons. 1, you get that red, green, blue manifestation. And 2, you get the 2 solfeggio numbers of 396 and 528. So to me, that makes 440 the winner. So I looked at convergent just intonation like I had shown you before. Those all line up with A, which I thought was kind of interesting because A has that interesting relationship between the recursives and the absolute as far as those key intervals go of the perfect fourth, perfect fifth, and the major second, minor seventh. And here, there is no octave in this tuning system where you get the true geometrical mean relationship. However, you do get tons and tons and tons of whole numbers when A is set to 432. In fact, you get all whole numbers after a certain octave, which is around the middle octave there, that 5th octave that we talked about. Everything there and above, whole numbers all the way up the scale. And you can see 432 is the clear winner here for generating whole numbers. There are some runners up, but they are definitely nowhere near as competitive. And we get a standard deviation here of 0.60, which matches the same error as Pythagorean tuning. So there's that. And then we get the best intonation. Once again, we're looking at that F octave. And this generates 6 whole numbers, which once again, when A is set to 432. And when we look at 432, it's definitely the best at generating whole numbers in this particular system. So of the 4 systems we looked at, 432 generates the most whole numbers out of 3 of the 4. Pythagorean, convergent, and the best fit intonation. Only the 5 limit just intonation does 432 just fall on its face, and 440 actually makes the most sense. Now remember, in equal temperament, 432 does nothing. So there's actually 2 tuning systems that 432 is completely meaningless in. 5 limit just intonation and equal temperament. Both of those, 440 makes the most sense. So let's look at my final table here. Here's everything. All the rational systems versus the irrational equal temperament. All of the recursive multipliers, and I've colored the recursive multipliers for which ones should fall on. If it's blue, it should fall on a black key, and if it's a different color, then it should be falling on a white key. And then I list which octave is the ideal octave for not having any expanded or contracted values in it, which means also that it would be in perfect geometric mean relationship, all of the intervals, with convergent being the only one that has no geometric mean interval in it. There's always going to be some value that's not going to be have a geometric mean relationship with its twin interval. However, that one's interesting in that A is the best octave to tune from, which we've already established that. For the other systems, F was the ideal octave and A was the octave that gave you some pretty ugly numbers. But in this one, A is the octave that all of your ideal numbers align with. So kind of interesting. They all use small fractions with the exception of Pythagorean. And the best value for tuning A for getting whole numbers, 3 of the 4 is 432. 5 limit just 440, but also equal temperament, I think 440 works the best. There's all of the standard deviations in comparison to equal temperament. 5 limit being the worst, Pythagorean and convergence being the second place. They tie, and then best fit just intonation gets you the lowest error, the closest standard deviation to mathematical purity. And then finally, just as an aside, I looked at light. And remember how I defined the maximum value of A being whichever tuning of A that gets you the closest approximation to that inverse relationship between a wavelength of light and the hertz of the keyboard. And for equal temperament, that was 432. Well, for these other tuning systems, it was different values for A. So for Pythagorean, you got the closest to that reciprocal relationship with A being 454, with 5 limit 449, and with best fit just intonation 453. And because convergence just intonation does not have any pure geometric mean octaves, we're not really looking at that as a comparison to light, because that's one of the requirements for, you need that pure geometric relationship between all of your intervals if you're going to compare it to that octave for where light intersects with sound that I was talking about in a prior video. But you can see there that best fit just intonation once again does the best job in all of its approximations to mathematical purity. So, I think I have said everything that needs to be said about these tuning systems at this point. Am I going to do a video on triads? No. No, I am not, because triads are just taking intervals and stacking them. I've talked about intervals. It's done. Am I going to look at musical tuning systems that use more than just 12 tones? No, I am not. I think that the 24-tone system is a lot of hot air. I don't think that it makes any sense. 12 is definitely the number that to me makes the most sense. And I think I've explained why in my first video. And once again, looking at the Fibonacci sequence, yes, there's a 24, there's a pattern of 24 here, but if you look closer, it's really 2 patterns of 12. And to me, the significance I find in that is when I talked about at the beginning, in order to find all the intervals for all of your notes, you need 2 octaves, because at some point you're going to have to cross into another octave if you're going to look at interval values. So that's where I see the significance of 24 coming into play, and the fact that you have 12 keys, but in order to find all the intervals, you need 2 octaves to do that, to span across. So that's the significance of 24. Not that there should be 24 individual tones. I think there should be 12 individual tones, and then you need 2 octaves to determine all of your intervals. So that's the significance of the 2 pairs of 12. Am I going to be looking at using a base other than base 10 for the numbers generated by musical intervals? No, I am not. If you want to do that, go for it. Have fun. I'm fine with base 10. I don't need to go any further with any of that as well. I think at this point I have discovered everything I was curious to discover when I started this project. And using mathematical system and other bases, it could very well show you some significant stuff that's, I'm not aware of, and I would think was interesting if I did learn about it, but I'm not going to be the one to go do the work. Base 10 works fine. I figured out what I needed to figure out. And what did I figure out? Well, here was kind of the questions that I felt like I had going into this that I have now answered for myself. The first question: everybody hates Pythagorean tuning because of the Pythagorean comma. Yeah, well, when you match recursive to the keyboard, there is one octave that gives you the Pythagorean comma. All the other octaves give you perfect fourth and perfect fifths. I don't think it's an issue. If you're tuning it properly, it's just one of those things where you can easily make music around certain intervals if you need to, if it sounds bad. And that's how Baroque and classical composers did music all the time. And their music sounds fine. All right, so which octaves have only default intervals with no expanded or contracted values? And we saw that for Pythagorean, that both the C and the F octaves are those two octaves, C being binary and F not yielding any whole numbers. So C is generally regarded as the octave that is preferable of the two. Why is the fifth octave on the area of the keyboard the best to tune from? In a prior video, I showed how that area of the keyboard is where you see an interesting conversion between the wavelength of light and the hertz of sound that I thought was interesting. So instead of starting at the bottom of the keyboard and tuning your way up, or the top of the keyboard and tuning your way down, we start in the middle of the keyboard and then we tune to the left and to the right. And I think that makes sense because of where that convergent point is between light and sound. Why is A the best note to tune from and not C or some other? Well, I mean, in this case, C might make a good tuning from because of the fact that C has that great octave with only the ideal intervals in it. However, we have established that the A octave is interesting and that we get those interesting alignments between key intervals and recursive values that I have talked about now ad nauseum. So I can see that being a reason why people wanted to tune off of A rather than any other of the notes on the keyboard. And then why is 432 the best number for A? And I have talked already about how 432 being the product of a power of 2 and power of 3 exclusively, it gets you the most whole numbers, which is nice and convenient. It's not magic. 432 in and of itself is just a number. It has no qualities beyond that. But in this tuning system, it leverages certain qualities that make it convenient for generating whole notes that have whole numbers, which in antiquity, it's going to be a lot easier to tune instruments tuning off of whole numbers than fractional numbers or repeating decimals or whatever. So it's mathematical, not magical. And what other things have I learned from doing this project? Okay, here I told you that I learned that 432, other than being mathematically convenient, is not magical. And in one of the tuning systems, 5-limit just intonation, 432 makes no sense at all. And it makes no sense in equal temperament. And what about the claim that A equaling 440 is a Nazi or Rockefeller plot to destroy our minds and make us physically ill? Well, I think I have debunked that. It's the only value for A that gives you a red, green, blue color match. And in 5-limit just intonation, it is the only value that gets you 2 solfeggio numbers, including 528, which is some magical heart number, right? And everybody loves solfeggio numbers because they're magical, right? Well, another question I feel like I have answered for myself is that solfeggio numbers are not magical. It's just a relic from tuning systems that people used in the past. And that's all. And I don't think there's anything magical of them other than in this tuning system, 5-limit just intonation, they pop up if you tune A to 440. So I would see that as kind of a code or something of that nature by people who have created music in the past, of basically saying, if you get these numbers in your tuning system, you know you tuned it correctly. And I don't think it goes beyond that. And isn't equal temperament a Nazi or Rockefeller plot to destroy our minds? No, it's mathematical perfection is what it is. And yes, it does have the drawback of being It only generates irrational numbers for its tuning system, but it is mathematical purity. It makes changing keys effortless. And for music, I think it is just fine. It, I think it sounds great. So then, why did I bother doing all of this? What was the point? Well, one, I hate misinformation, and I hate all the ridiculous New Age claims about tuning systems for music and values for A that nobody ever offers any evidence for. And I wanted to see what the reality was, and I wanted to test claims, and I wanted to find out for myself what is significant about this, if anything. And I hope you will agree with me that there are some interesting things there to be found in each of these tuning systems, and for certain values to tune a to. But I don't think they're magical. And will music sound any better than any of these systems versus equal temperament? I don't know. I'd like to try. At some point I'll get a synthesizer and that is able to be tuned to high granularity frequencies that I can try this out with, and make sure that all the sound waves are in phase and all of that. I don't know if it'll sound any better, but my interest in this is beyond music, though. I actually am very fascinated with cymatics and also just using frequency in ways other than music. For instance, I don't know if you have seen a documentary about the caves in Barabar, India, but their shapes and their geometries and their mathematical relationships are very, very, very interesting and fascinating. And there is an association between the numbers that can be found within those caves and music. And those caves also generate resonant frequencies. And I think that's on purpose. I think whoever made those caves to begin with were trying to do something where they were using frequency in non-musical ways to achieve some kind of effect. And I find that very fascinating, and that's why I wanted to do this. Because remember, the biggest drawback of equal temperament is that you don't generate whole numbers or rational numbers. Everything is based on irrational numbers, which for music, you'll never know. It's fine. But if you want to do actual work, like industry or manipulation, then leveraging the rational qualities of music is going to be far more effective. So for instance, there is some evidence that when a cat purrs, it's actually aiding in its healing factor versus if it didn't purr. That's one of the things cats have evolved. So it makes me wonder, is there frequencies that might accelerate healing factor in humans? And I'm not talking about sound bath crystal bowl healing. I'm talking about actual scientific evidence of using frequencies targeted in certain ways to create certain effects within the body. And we know this happens because we've used sound waves to do things like obliterate gallstones. We have toothbrushes that use frequencies to help clean your teeth better than brushing alone would. So we know that frequencies do have usefulness, and I bet there's a lot more. And that's why I wanted to do this. Ultimately, my true reason for wanting to do this is because I wanted to see what are some of the relationships between musical tones and intervals, and how they might be paired in ways that might be more effective than equal temperament would be able to do because of the nodal clarity, the nodal precision that happens in rational sound waves. Now, what do I mean by that? So if we look here, here's Pythagorean tuning. So the red sound wave there is set at a value of 1. So it's a sine wave that will make one full, up and down, and then it will, by the number 2 on that scale there, on the x-axis. And then what I've done is I've overlaid on that red unison sine wave there each of the Pythagorean ideal interval fractions. And what you can see is the blue sine wave is the interval, and if we look at the top, it starts to spread out and then it slowly converges back to where it will meet the unison again. Now in that top one, that fraction's pretty ugly, 256 over 243. We don't actually have any pure nodes on that one until we get way, way up the scale. But if we look at the next one, 9 over 8, we get a node right there at 8, which is 8, negative 2. And only pay attention to the first number. The negative 2 means I had to shift the sine wave down so that I could list all the sine waves one after, one on top of the other. So the y value you don't need to pay attention to. It's the x value that's the important one. We get a node at 8 where we get a purely destructive nodal point where the unison wave and the interval wave essentially cancel each other out perfectly. And then if we move up the scale some more to 16, we see where both waves converge perfectly at 16. So those are called nodes. And you have constructive nodes or destructive nodes, right? Destructive nodes are where it's canceled out. And constructive nodes are where it's actually amplified at its most intense point. If we look at 32 over 27, we get, mismatches until we get to 27, and then we get a purely destructive node point. Now, if we look at 81 over 64, we don't have any pure nodes because we don't get our first one until, if you've noticed the pattern, until we get to 64, where we would get our first purely destructive one. Which isn't to say that there is some destructive interference happening in these intervals, but there's always going to be some leverage one way or the other, where one wave is going to be slightly dominating the other wave. We don't get that pure cancellation until we get to the 64th iteration. Okay, so 4 over 3, we get pure constructive and pure destructive nodes very, very rapidly, and I'm only showing you the first two. That would span the whole interval of those two waves. The tritone, we don't get anything good until we get to the 512th interval, so it's way down the line. Once again, we get some destructive and some constructive, but nothing that is a pure cancellation or at all until way down the line. 3 halves, once again, like the 4/3, we get them fast and we get them regular. So anyway, you can go down and you can see how that works. If we look at 5-limit just intonation, we get a lot more destructive and constructive nodes a lot quicker and with a lot more frequency. So if you wanted to do work with sound, such as acoustic levitation or targeting certain, whatever, you would want to leverage this quality in order to take advantage of purely destructive and purely constructive node points. And then if we look at the best fit just intonation, once again, lots and lots and lots of pure nodal points of constructive or destructive waves, wave interactions between a unison and some kind of an interval fraction. And as I mentioned before, doing things like acoustic levitation, it leverages those constructive and destructive wave nodes in order to create pockets where you can actually levitate something. Okay, so this isn't magic. I'm just telling you that when you use rational number music systems or sound systems using certain particular fractions, you can leverage that to actually do other things than just play music. And that's what I'm actually more interested in. So that's it. I think I have talked long enough about this subject. Once again, I am not a mathematician and I am not a musician. I'm just somebody who is interested in music and knows how to run a spreadsheet and knows how to calculate some basic arithmetic and wanted to challenge some garbage assertions that people have made about tuning systems and tuning values. And, you know, I feel like I have a pretty sound understanding of the subject now, and that I can tell when somebody is a charlatan now. And I hope anybody watching this video up to this point, which good for you. Oh my God, this is, you are a trooper if you've watched all of these videos. I hope you have learned something too that will help you be more immune to a lot of the misinformation that gets peddled out there on YouTube and Gaia Television and all of these other places that will just give a microphone to anybody that will say anything without any evidence. And then wrap it up with some unity consciousness talk, I guess, to make you feel good and make their misinformation sink in even deeper. Don't fall for it. Trust your math, trust evidence. Don't trust anybody that doesn't show you information that you cannot replicate. And I hope you have a wonderful time with this information. And I hope you had a wonderful time learning about it with me. I put this here for me so that I have it here for future reference for myself. But anybody that wants to reference it, that's why I put it out. Because why not? It's my gift to whoever this would be meaningful to. All right, that concludes the musical series. I'm going to start doing some other videos on math in the coming future as I find time. Thank you very much.